Welcome everyone to this webinar from Sydney. My name is Felix Teska and I'm a Senior Technical Officer for atom probe sample preparation at Sydney Microscopy and Microanalysis. I very much appreciate Tescan and CAMECA for giving me the opportunity to talk today about advancing atom probe sample preparation with the AMBER X2. As you can see, this has been a collaborative effort between staff at Sydney Microscopy and Microanalysis, as well as researchers at the University of Sydney, the University of New South Wales, and Nanyang Technological University in Singapore. As an overview, I would like to begin by introducing Sydney Microscopy and Microanalysis, followed by the requirements around atom probe sample preparation using FIB-SEM tools. After this, I want to show 4 different case studies that we have completed with the AMBER X. Those will focus around the targeting of phase boundaries in a high entropy alloy, targeting intermetallic particles in an additively manufactured aluminium alloy, as well as studying impurity and dopant distributions in different solar cells. To conclude, I want to give a brief summary and a short outlook. Sydney Microscopy and Microanalysis is a multi-user facility that supports research at the micro, nano and atomic scales. In the bottom left you can see the Madsen building, which has the longest history on campus. That's where you can find electron and ion microscopes, as well as light and X-ray imaging tools. That is also where the LEAP and Enviso atom probes are located. The Charles Perkins Center supports cellular imaging, and the Brain and Mind Center supports neuromicroscopy. In the Colling Institute, cell and omics imaging are provided. The Sydney Nanoscience Hub allows nanoscale electron microscopy using aberration-corrected STEMs. The latest addition is the Engineering and Technology Precinct, supporting engineering microscopy, and that is where you can find the AMBER X2. In the future, there will be a biomedical accelerator supporting functional microscopy. Sample preparation for atom probe tomography using FIB-SEMs generally aims to produce very sharp, needle-shaped specimens, as you can see in the bottom left schematic. On these specimens, different types of experiments can be conducted, such as field ion microscopy, field electron emission microscopy, or field absorption microscopy. However, most popular nowadays is atom probe tomography. On the bottom right, you can see the secondary and backscatter electron micrographs of a readily prepared atom probe sample. Generally, a tip radius of less than 100 nanometers is desirable, and this can be measured during the preparation process or by achieving electron transparency at around 5 kV electron beams. For most materials, a Schenck angle of less than 10 degrees is desired too, and the sample has to have a smooth surface that is free of any voids or protrusions. Finally, it is necessary to retain a minimal amorphous damage layer and minimize ion implantation to keep the sample in its original condition. On this slide, I would like to show why we need to produce such sharp needle-shaped specimens. On the left-hand side, you can find a crude schematic of how an atom probe works. The specimen is placed in an ultra-high vacuum and cooled to cryogenic temperatures, which are usually around 50 kelvins. It is then placed in front of a local electrode, and a standing field is applied between specimen and the local electrode. This is necessary so that via voltage pulsing or laser pulsing, individual atoms can be detached and become ionized. These ions are then accelerated through a mass spectrometer where the time of flight is recorded as an identifier of the elemental species. At the end of the mass spectrometer is a position-sensitive detector, so that the X and Y coordinates, as well as the ion sequence number, can then be used to generate a 3-dimensional compositional map. This is a destructive process. On the right-hand side, you can see the difference in field of view compared between a local electrode atom probe and an in viso atom probe. This is achieved by a slightly different placement between specimen and local electrode. More details about this arrangement you can find in the reference below by Tech and colleagues. To introduce my 4 different case studies, I would like to begin with the phase boundary characterization, followed by different challenges in different materials, such as intermetallic particles, dopant distributions, and impurity segregations. On the left-hand side, you can see the SEM team at Sydney Microscopy and Microanalysis being excited about the new AMBER X PFIB. From right to left, you can see Vijay, who is the SEM manager, Lena from AXT, Asha from SMM, and Ruth from AXT, and myself included. The first case study I would like to share is on the phase boundary characterization of a high entropy alloy that's been produced by additive manufacturing. Through this manufacturing route, it is possible to produce near net-shaped components which can be complex in their geometry. Rapid solidification rates allow the suppression of micro and macro segregations. That's important because high-entropy alloys contain multiple principal elements in near equiatomic ratios. And this is necessary to achieve a synergy between strength and ductility while improving corrosion and irradiation resistance. On the top right, you can see an exemplary micrograph how the microstructure of such an alloy looks like. To learn more about the metallurgy of these materials, I recommend to follow the work by Shubo Gao, who was at Nanyang Technological University at the time and is now with A-Star. For this sample, we have chosen the most conventional approach by protecting the region of interest with an electron beam platinum deposition, as you can see in the top left micrograph. This platinum cap is then reinforced with a low energy ion beam and tilting the sample to 55 degrees. To fabricate a wedge-shaped specimen, we would then undercut our region of interest with a 30-degree inclination. This is achieved by tilting the stage to 25 degrees and cutting it from both sides. The specimen can then be picked up using the OptiLift micromanipulator at a 0-degree stage tilt, and the lift out is long enough to fabricate an entire batch of 4 to 5 specimens. This is done by placing the wedge-shaped lift out above different tungsten posts, attaching it and sectioning it into the batch. Each tungsten post is then tilted into the ion beam and annular milling is conducted to generate a needle-shaped specimen, as you can see in the top right corner. We also used an EBSD camera to support end pointing with transmission Kikuchi diffraction and less than 10 nanometer accuracy. On the left-hand side, you can see an SEM micrograph of a readily prepared atom probe specimen of this high entropy alloy. The initial tap radius and shank angle are both acceptable. The corresponding TKD map is shown in the second column, where face-centered cubic grains are colored in blue and body-centered cubic grains are colored in red. I then took this sample to the in viso atom probe to capture almost the entire volume shown by the TKD map. Here you can see a rotating animation segmented in corresponding colors of the FCC and BCC grains. Thanks to this large volume, we can analyze the interface between these different crystal structures in great detail and find, for example, very small segregations of nickel along their interfaces. My second case study is on the impurity distribution of a solar cell that has been negatively doped using phosphorus. These modern solar cells are often complex assemblies of a silicon substrate, different doped layers, thin films, and various types of contacts. All this is necessary to improve the efficiency while ensuring manufacturability. However, high humidity conditions can often deteriorate the performance over time, so that the service life is often a function of potential contaminants which can react with the environment. On the right-hand side, you see a micrograph of what these solar cells look like on the micron scale. However, to learn more about their functional properties, I recommend to follow the work by Hao-Ran Wang and Chandani Sen from the University of New South Wales. For this work, we chose a similar approach to the first case study by protecting a region of interest with an electron beam platinum deposition. However, a smaller batch size was required so that we could restrict the deposition to a smaller area. Again, we would reinforce this platinum deposition with a low energy ion beam deposition, as shown here. As a next step, we would proceed by undercutting the sample surface with a 25-degree stage tilt to generate a wedge-shaped specimen, which is then picked up using the micromanipulator at a 0-degree stage tilt, as shown here. As long as the sample is reasonably flat, that is no problem. To study the surface contaminants as well as their progression into the bulk material, we chose again an analysis direction perpendicular to the sample surface. We therefore sectioned the lift out into a small batch of 1 to 2 specimens by attaching them on tungsten posts, as shown on the right-hand side. Each tungsten post is then again tilted into the ion beam for annular milling. However, to ensure that our atom probe data would measure from the surface into the bulk material, we targeted to remain a small platinum patch on the very apex. This can be seen on the top right micrograph. On the left-hand side, you can see a SEM micrograph of a readily prepared specimen. You can see there's a very small platinum cap retained on the surface, followed by different layers into the bulk silicon substrate. Next, you can see an atom probe reconstruction with the full field of view, where we now can follow the oxide surface, a phosphorus doped layer, a buried oxide, and the silicon substrate. Due to the irregular shape of the surface oxide, we decided to restrict the analysis to a center core region with a cylindrical region of interest, as shown here. This allows to extract a sharp one-dimensional profile from the surface into the bulk of the solar cell. And tracing potential contaminants as well as dopants shows very heterogeneous distributions depending on the depth coordinate. In this third case study on intermetallic particles in an aluminium, copper, cerium, zirconium alloy, we are going to take a somewhat different approach. This material has been additively manufactured as to produce a high volume fraction of intermetallic particles. You can see that on the right-hand side micrograph, where the intermetallic phase in bright forms dense networks. This allows operational temperatures of up to 400 degrees centigrade. The intermetallic phase itself is rich in aluminium, copper, and cerium and allows the dissolution of some zirconium. Through additive manufacturing, the cellular network that's formed by this intermetallic is a function of the local thermal history, as we can see a morphology change between melt pool boundaries and melt pool interiors. To learn more about these manufacturing processes and the properties of this material, please follow the work by Kevin Sisko and Kirk Chen. Here we would take a somewhat less common approach to target a region of interest with a known location relative to melt pool interior and melt pool boundary. As you can see in the top left micrograph, I would only mark the region of interest using electron beam platinum deposition and skipped the reinforcement with a low voltage ion beam. The undercutting was also performed at no stage tilt, producing a much more shallow wedge, as you can see in the second row. Regardless of the wedge geometry, it is possible to complete the lift-out using the OptiLift micromanipulator. However, in the next step, we would rotate the manipulator by 90 degrees around its axis to produce a specimen where the analysis direction now follows the sample surface plane. This specimen is then attached to a tungsten post, as shown here, and annular milling follows as usual in the other approaches. However, here, backscatter contrast imaging allows us to keep track of the intermetallic morphology and identify the melt pool interior and melt pool boundary during the sharpening process. On the left-hand side, you can see an exemplary SEM micrograph of a readily prepared specimen after low voltage cleanup. The matrix and intermetallic can be distinguished by brightness variations in the backscattered electron contrast. After taking this sample to the in viso atom probe, we could generate 3D atom maps of aluminium, copper, cerium and zirconium, as shown in the second column. Using a 15 atomic % copper iso concentration surface, we can further segment the data now into matrix and intermetallic and perform compositional analysis of their interfaces. For example, here we found that some slight enrichment in copper occurs on the interface of the intermetallic phase. My fourth and last case study I would like to share today is on the boron dopant distribution in a solar cell. This is a thin film solar cell, as you can see on the right hand side. And here, thin films are often used in different sequences as absorber, buffer, whole electron transport, or passivation layers. There are several advantages to these devices, for example, the efficient use of scarce materials and improving the conversion efficiency. And these thin films are often synthesized by a combination of chemical vapor deposition and physical vapor deposition sputtering. However, that means that any new technologies or innovations must be suitable for direct mass production. More details about these devices you can find in the work from Shuo Deng and Ning Song from the University of New South Wales. For this sample, our first preparation steps followed standard procedures. We would protect the region of interest using an electron beam platinum deposition and then reinforce the protective platinum cap using a low voltage ion beam, as shown in the top two micrographs. However, in the next step, we would deviate from a pre-tilt stage of 25 degrees. Instead, I performed the first cut at 50 degree stage tilt and then performed the second cut at 0 degree stage tilt. This is to ensure that any thin films have an orientation that is inclined to the analysis direction to ensure a smooth transition for layers of different field evaporation properties. This inclined wedge is then lifted out using the micromanipulator at a 25 degree stage tilt, as shown here. After this, the lift out is segmented into a batch of specimens, producing several inclined wedges, as you can see in this micrograph. The annular milling follows conventional procedures, creating a tip-shaped specimen, as you can see in the last micrograph. On this slide, you can first see a specimen readily prepared from this inclined wedge geometry. Initial tip radius and shank angle are both acceptable, so that we took this batch of sample to the in viso atom probe. This allowed us to acquire a full field of view reconstruction, as shown in the second column. Here we can identify boron-doped silicon, a borate oxide layer, and the silicon substrate. Special attention had to be paid to the buried oxide layer and the dopant distribution in its proximity. And while we were successful in ensuring a smooth transition between the different layers, we had to restore the oxide morphology as close as possible to its original condition in the reconstruction. Here, CAMECA's IVAS offers a landmark registration tool to flatten the oxide layer, as you can see in the third column. Using this data, we could then extract sharp 1D concentration profiles showing us where boron and oxygen are located. To conclude, the AMBER X allows time-efficient specimen preparation for atom probe tomography. This is due to its ion optics generating well-defined ion beams at high and low voltages, allowing accurate and fast milling operations. Together with the in vitro atom probe, that makes a powerful combination to study functional and structural materials. The OptiLift micromanipulator facilitates standard lift-out as well as 90 degrees rotated or even inverted specimen preparation. The drawbeam pattern management tool allows to make your own recipes, which then can be shared with novice or experienced researchers. In the next months, I want to attempt to simplify the preparation of robust atom probe specimens by using Tescan's expert BI Python libraries and visual coder tools to make our own patterns and then test them autonomously. I would like to thank you for joining this webinar and thank you for your attention. I would also like to acknowledge the support by my colleagues at Sydney Microscopy and Microanalysis, Microscopy Australia, who are supporting many facilities and staff like myself across the Australian continent. I would also like to thank CAMECA and Tescan for having the opportunity to talk here today.
Hi everyone, I'm glad to be part of this webinar, where I can introduce the role of new Tescan AMBER X plasma FIB-SEM for atom probe sample preparation. I'm Martin Slama, Product Marketing Manager for FIB-SEMs in Material Science at Tescan. Before we will start with the results, let me introduce you to Tescan AMBER X and explain you why this tool is so special. For years, labs working in material science have faced a fundamental limitation, choosing between precision and throughput. Gallium FIB-SEM systems have been the standard for high-precision tasks like TMLR preparation or nanofabrication, thanks to their finely focused beam. But that same gallium beam can cause contamination and material interaction issues, especially with sensitive samples, making it less ideal for certain workflows. On the other side, plasma FIB-SEM systems, especially xenon-based, have been the clear choice for high-throughput applications like large volume 2D and 3D characterization. Their speed and efficiency make them indispensable when time and scale matter. The trade-off, he has always been precision. Plasma systems have historically struggled with imaging quality at low kV, background beam noise, and the level of control needed for fine detailed work. As a result, many labs have had no choice but to operate both types of systems. It's a workaround, but one that comes with added complexity, cost, and redundancy, because no single tool could meet the full range of demands. That challenge is exactly what inspired us to rethink what a plasma FIB could be. We went deep into the core limitations and began pushing the technology further, refining beam quality, improving low kV resolution, and minimizing the noise and once limited precision. Our goal wasn't just incremental improvement, it was to break the compromise altogether. That work led to the development of AMBER X2. It's not just an iteration, it's a leap. AMBER X2 is the first system to bring together the precision needed for high-quality TMLR preparation and the throughput that plasma FIB is known for. It's fast, it's accurate, and it's intelligently automated to shorten time to data. AI-driven routines enhance repeatability and simplify complex tasks, making the entire workflow smoother and more productive. What this means in practice is simple. You no longer need two systems to do high-end materials characterization. AMBER X2 handles it all, from delicate nanoscale prep to large volume analysis and even fabrication, on a single optimized platform. It gives you the precision you've always trusted with the speed and flexibility you've always needed. This is the best of both worlds, brought together in the one tool for the first time. This system was introduced last year, and journey continues with the collaboration with the University of Sydney. They are producing these nice results either for TM sample preparation or atom probe sample preparation. But also this year, the system won the R&D 100 award, especially because of the new Mistral FIB column, plasma FIB column performance. Our focus to atom probe sample preparation, I'd like to briefly highlight one of the traditional strengths of plasma FIB-SEMs, large volume characterization, whether through 2D cross-sections or full 3D tomography. When comparing 3D characterization capabilities between gallium and plasma FIB-SEMs, the difference in throughput is quite significant. With the gallium system, acquiring data from a volume of around 30 by 30 by 30 microns can take roughly a day and a night. In contrast, a plasma FIB-SEM can cover a much larger volume, approximately 100 by 100 by 90 microns, in about a similar time. That's nearly 2.8 times more volume, enabling more comprehensive datasets in the same overall time frame. By complementing traditional techniques like EDX with additional analytical methods, we can significantly expand the utility of the system. The 3D FIB-SEM tomography visualization illustrates how 3D EDS can be combined with 3D TOF-SIMS data acquired during a single run. This integrated approach provides richer insight into sample composition, for example, mapping, lithium distribution, or identifying specific isotopes. More broadly, 3D FIB-SEM tomography, especially when applied to large volumes, helps reveal how structural and compositional features are interconnected, offering a deeper understanding of material behavior. So far, I've been speaking about traditional applications of plasma FIB-SEMs. TM sample preparation or atom probe sample preparation, however, has remained a significant challenge not only for plasma systems, but even for gallium FIB-SEMs, especially when dealing with demanding materials and preparing the samples for high resolution STEM or TM imaging at the crystal lattice level. Success in these applications depends heavily on minimizing damage introduced during the final polishing steps. The goal is to preserve the material's pristine structure while achieving extreme thickness, typically below 50 nanometers. In many cases, samples need to be as thin as 30 or even 20 nanometers to meet the requirements of the advanced imaging. Equally important is the ability to produce such high-quality samples consistently and repeatably, ideally in the way that doesn't depend on a deep FIB-SEM expertise, so even less experienced users can contribute to meaningful results in their research. It's worth mentioning that other approaches also exist to reduce gallium implantation artifacts. Just few months ago, we hosted a webinar focused on such solution. In the collaboration with Technor Glinda, we introduced an integrated gentle ion beam system as an alternative method for high-quality TM sample preparation. This webinar is available on demand on our website, so if you are interested in exploring alternative techniques beyond plasma FIB-SEM, it's valuable research with practical insights into how low damage polishing can be achieved using inert ions like argon. Also, a few months ago, we had the opportunity to discover how Tescan AMBER X2 can work for TM sample preparation. This webinar was again done with Uni Sydney, and it's also available on demand on our web page. Let's dive deeper to the atom probe sample preparation. So let's start with the challenges. So the first challenge is the overall quality. It could be dimensions, the shape, and also the potential damage the atom probe tips. There is also demand to prepare such samples at cryogenic conditions for beam-sensitive materials. Also, one of the challenges is to make the atom probe sample preparation more routine or even automated. And the last challenge that we see is to be able to access the sample details from the desired orientations, meaning that we are targeting a really small area, and we during the preparation we don't want to miss the area of interest. And for that, we have to think a little bit outside of the box how to prepare such of the samples and maybe change the geometry. And I will explain that on the following slides. Start with the first challenge, and I want to explain what makes atom probe sample preparation or even TM sample preparation difficult with the plasma FIB-SEM and how Tescan AMBER X2 is changing the game. Additional concerns about plasma FIB-SEMs arise from differences in beam profiles compared to gallium FIB-SEMs. Plasma FIB beams tend to have a more Gaussian shape, larger spot sizes, and more pronounced beam tails. These characteristics create trade-offs in TM sample preparation, as discussed in the publication by Suzy Vitali and Josh Sugar, comparing gallium and xenon plasma FIB-SEMs. Such trade-offs increase process complexity, which can present challenges for broader adoption, often requiring specialized expertise. Example of this complexity is the higher polishing rate of the protective deposition layer, caused by the more intense beam tails of plasma FIB-SEMs. When the sample becomes thin, this effect can result in a wedge-shaped lamella or more pointy deposition on the top of the atom probe tip, which in turn accelerates the sputtering of the protective layer. One way to mitigate this is by depositing a thick layer. However, this introduces its own challenges, particularly in achieving the desired final thickness or good shape of atom probe tip. All these factors, layer thickness and the sensitivity to beam tails, contribute to the increased complexity of TM sample preparation or atom probe sample preparation on conventional plasma FIB-SEM. Ultimately, these trade-offs stem from the inherent characteristic of the plasma FIB beam profile. Here, when we launch the Tescan AMBER X2 powered by Mistral, we claimed that we stated that we redefined the FIB-SEM market primarily due to its advanced FIB beam performance. With significantly improved resolution, we can now navigate with greater precision and achieve higher beam placement accuracy, which is critical for application like TM sample preparation or atom probe sample preparation or nanofabrication. From the image on this slide, you can also observe the comparison of beam profiles at equivalent picoamperes range. It's apparent the Mistral's beam profile at this current closely resembles the benchmark profiles of gallium FIB-SEMs, especially in terms of sharpness and minimal beam tails. This similarity is one of the key reasons why we can now apply plasma FIB-SEM technology even the most demanding use cases like either TM sample preparation or atom probe sample preparation. I've mentioned the low kV resolution is critical not only for TM sample preparation but also for atom probe sample preparation, which is important for the precise beam placement. Tescan AMBER X2 equipped with the Mistral plasma FIB column delivers resolution comparable to some gallium FIB-SEMs currently available. In fact, when comparing imaging capabilities with the 9-year-old gallium FIB-SEMs, Tescan AMBER X2 achieves even better resolution, showcasing the evolution of plasma FIB technology. Mistral column, we are directly addressing many of the long-standing challenges seen with conventional plasma FIB-SEMs. One of the most important improvements is the beam profiles itself. By refining it, we are now able to better protect the deposition layer during the thinning, which is something that used to be a common difficulty. These improvements bring the overall milling behavior much closer to what we know and expect from gallium FIB-SEMs. That means we can now adapt a more straightforward and familiar approach to TM or atom probe sample preparation without the need for complex workarounds or adjustment. And it's not just about beam shape at high voltages. Mistral delivers consistent beam quality and placement accuracy across the entire voltage range. This allows us to comfortably carry out low kV polishing steps, which are essentially for minimizing damage and achieving the thin, high quality TM samples researchers are aiming for. Let's move now to another challenge, which is the atom probe sample preparation at cryogenic conditions. The idea behind the cryo process is that it ensures that the material's original state remains intact throughout the FIB sample preparation. Basically, cryo atom probe preparation allows us to work with samples under cryogenic temperatures, minimizing sample damage while maintaining sample chemical stability. One of the main benefits is reducing the risk of damage and chemical changes during the FIB milling process, but it also introduces specific challenges. For example, gases from the gas injection system behave differently at cryogenic temperatures, often requiring adjust workflows or alternative approaches to avoid unwanted deposits. To the left, you can see an important distinction. Unlike a regular GIS site-specific deposition, the entire surface has been covered with platinum by GIS. This approach is typical for cryo-prepared samples. In the next step, we've prepared a sample within a trench. Notice the two uncovered sections. These are intentionally left as attachment points for the needle, providing a precise alternative to GIS attachment. Now turning to the two images on the right-hand side, you can see the process unfold. Using a cryo manipulator, we carefully approach the sample and mill away a section of the bulk material. This step allows us to securely attach the nanomanipulator to the specimen and release it cleanly, ready for the next stage of analysis. I want to cover is workflow optimization. About the workflow. It's about ensuring that every step in the process is precise, efficient, and adaptable. In FIB-SEM workflows, there are key challenges often arise. First, how do we maintain resolution when working with the many small specimens in large fields of view? Second, how can we standardize processes? Many workflows developed in the past can be predefined, saved, or shared, which affect consistency and scalability. And third, how do we enable flexibility? Standard modules often limit customization of workflows, making advanced or unique tasks harder to accommodate or accomplish. These are the challenges we've tackled, and on the next slide, I'll introduce some of the other possibilities regarding the automation. We can divide the modules for the automation to the robust and to the more flexible one. The robust one, they are for dedicated applications, or like for 3D slice and view, 3D FIB-SEM tomography, or for example, automated TEM sample preparation. The other modules enable more flexibility, like for example, DrawBeam Automate, which works based on a recipes batch processing. The other step is to use the Python script to generate or to write your own recipes, or you can also use the stream files for some patterning applications. So looking more closely to the potential of some new application developments, there's also possibility to use the visual coding to prepare your Python scripts that can be later transferred to the custom GUI application that again reflects more the robustness. The last challenge I want to address before Felix will take it over is how we can transform the sample's geometry to access new details. As a first, let's discuss the specialized approach that's often necessary for challenging analysis, like inverted specimens. This technique addresses specific limitations in traditional workflows and offers unique advantages for complex materials and semiconductor devices. So what is an inverted specimen? It's a sample prepared by reversing its orientation, typically by 180 degrees from the standard position. This approach might seem unconventional, but it's a game changer in many scenarios. By using an inverted specimen, the main reason is to gain optimal access to regions of interest. By flipping the sample, we can better target specific areas while minimizing damage to surrounding structures. Inverted specimens help preserve the integrity of the sample during analysis, which is vital for sophisticated material systems or semiconductor devices. These are cases where the surrounding materials often have significantly different evaporation fields, creating challenges for standard workflow. And during the Felix part, he will introduce the other approaches, not only the inverted specimen type. The challenges of achieving a proper 180-degree rotation, let's explore Tescan invention, repositioning and rotating nanomanipulator below the focus ion beam column. In the image left, you see the conventional setup where the nanomanipulator is positioned at an angle relative to the FIB. This setup limits its ability to achieve the precise flip needed for inverted specimens. Now, in the image right, place the nanomanipulator directly below the focus ion beam column, aligning it more perpendicularly to the sample. This positioning allows for accurate 180-degree rotation, perfectly aligning the inverted specimen as intended. An inverted specimen may sound simple, just rotate it to 180 degree, right? But in practice, it's far more challenging, especially with regular rotation manipulators. So let me show on this video why. If you approach the sample from the side as you would with conventional manipulator and rotate it 180 degrees, the resulting geometry and orientation are completely different from what's needed for a proper inverted specimen. So take a look at this visualization, and you can see the orientation of the specimen after 180-degree rotation. So now let's compare it to the our solution with the Tescan AMBER X, which is positioned below the FIB column. So after the sample is released from the material, we can freely rotate the specimen at 360 degrees. So it's not only dedicated for the inverted type of specimen, but for also different orientation. In this case, it will show the rotation by 180 degree, wearing the inverted type of sample, and the sample then can be easily attached to the grid or to the coupon for atom probe sample preparation. So now let's see how this adjusted workflow looks in action. So on the left, you see the SCM live window, and on the right, the FIB window, giving you a clear view of the process. What's remarkable is that this workflow was performed by one of our operators for the first time, highlighting just how simple and intuitive this methodology is. Instead of approaching the specimen from the left side, like in a conventional workflow, you approach it perpendicularly from the top. This allows seamless and precise rotation of the specimen by a full 180 degrees. In the video, you can see how the adjusted nanomanipulator setup enables effortless specimen rotation while keeping it fully protected. This workflow not only simplifies the process but also ensures high-quality results. Unlike conventional workflows, this setup eliminates the need to vent the chamber or manually reposition the sample. Instead, it follows a standard preparation process with one critical enhancement. You can rotate the specimen freely to your preferred orientation without any interruptions. This capability can be a game changer for atom probe analysis. And as you see, you can also, once the sample is still on nanomanipulator, you can polish out the deposition to prepare the best conditions for the attachment of the atom probe tip to the coupon. So let me sum up this for now. So we all would agree that the lift-out process is a critical step in all type of sample preparation, not only atom probe sample preparation. And our approach makes it more sample-oriented and efficient. With 360-degree rotation capability, you can easily adjust the orientation to suit material analysis needed, ensuring optimal alignment for the next stages. By positioning the nanomanipulator in the below FIB configuration, we have streamlined the workflow. This setup reduces unnecessary steps, does not disrupt the process by chamber venting or vacuum disruption. So let me just summarize my part. So Tescan has special solutions for the atom probe sample preparation. It can be used, for example, as was already mentioned, the Tescan AMBER X is the easy way how you can transfer the geometry of your sample for more advanced use cases. And following part, you will see some real-life examples. We also have the cryo workflow compatibility, so we can prepare the samples in the standard conditions or the cryogenic condition as well. There's a possibility to streamline the workflow using some of the automated workflows as the Tescan Beam or Tescan Visual Coder to simplify the workflow. And most importantly, Tescan AMBER X2 is the universal platform for sample preparation. That is not only the plasma FIB for the high throughput analysis, but also with improved resolution and beam profiles, it's more suitable for the precise application. Not only TM sample preparation, but also the atom probe specimen preparation, as you will just witness in a few minutes or more, like seconds. So it is. I would like to thank you for your attention, and now I would like to let Felix to take it over. Thank you very much.